Hi, I'm Hugo Bown-Anderson, and welcome to High Signal. Today, I have the privilege of speaking with Andrew Gelman, a professor of statistics and political science at Columbia University, and one of the leading figures in the field. Andy's work spans areas such as Bayesian statistics, causal inference, and the intersection of data science and the social sciences. He's also the author of several foundational texts in statistics and an advocate for making statistics more accessible and impactful in real-world applications. So, in today's episode, Andy and I focus on the practical side of data science. He emphasizes the importance of high-quality data, computational skills, and simulations over pure statistical theory. We discuss real-world applications, such as predicting election outcomes, and how causal inference plays a critical role in decision-making. Whether you're a data science practitioner or someone interested in the future of statistics, in my humble estimation, this episode provides clear takeaways into how we can better understand and work with data. Let's dive right in, starting with Andy's thoughts on the balance between computational skills and statistical theory.
I have a rule now. I don't like to ever gather data until I've simulated data first. And it takes work to write a simulation. I always say this, that to analyze data is like playing SimCity, and to simulate data is like writing SimCity. So it's more work, but it's worth it every time. It's the kind of work that makes you think harder about the problem. So, for example, if I simulate data, I need to define a population and simulate a sampling mechanism. So I have to make a kind of call, how different is my sample going to be from my population?
Next, Andy talks about why data scientists should think like coders when working with statistics.
Just as in coding, they always say never write the same code twice. If you're going to do that, wrap it in a function. But that's true of statistical procedures too. Do not think that whatever you're doing only once. Assume you're going to be doing it more than once. Partly that means documenting it and all that, but also it means thinking about what it means. It means thinking about what its inputs are and so forth. So that's like thinking like a coder in some way.
Lastly, Andy emphasizes that statistics is always about comparison. Here's why that's so central.
Statistics is always comparative. That in statistics textbooks, they'll sometimes set up a problem. Your goal is to estimate theta, something. Your goal is never to estimate something. Your goal is to compare. If it's not causal inference, you're comparing two groups, or you're comparing men to women, or you're looking at changes over time, or you're comparing different countries. It's almost always going to be a comparison of some sort. Be aware of that.
And before we get into the full conversation with Andy, let's take a quick moment to chat with the team at Delphina, who make High Signal possible. I'm here with Jeremy and Duncan, the co-founders of Delphina and producers of High Signal. Jeremy, Duncan, maybe you can tell us a bit about what you're up to at Delphina and why we're doing this podcast.
Thanks, Hugo. At Delphina, we're building agents for data science, and we've noticed there's a lot of noisy advice in data science. By nature of our work, we speak with a lot of interesting people in the space. And so with the podcast, we're looking to identify and share the high signal.
Awesome. And speaking of high signal, this episode is with one of the highest signal, in my humble estimation, out there, Andrew Gelman. And from the clips we just shared, I was wondering what in there resonated with both or either of you.
So for me, the discussion of simulation, accurate simulation, reminded me, or made me think of the problem of your evaluation harness in a machine learning project, and how important it is to get that right and to have it aligned with the problem you're actually trying to solve. In preparation for Delphina, I spent a lot of time talking to Kaggle grandmasters and other scientists and reading through interviews. And one of the things I've heard over and over again from successful experts was the importance of investing up front in having an evaluation harness for your model that accurately reflects what you're ultimately trying to predict. In the context of Kaggle, that meant aligning with a leaderboard. In business, it means aligning it with the business outcomes you're trying to affect. And if the evaluation harness is not robust, not reliable, then you'll end up in the wrong place with your model. And so a lot of thought and effort into that up front pays dividends.
Absolutely. And a lot of it is the real work that we all have to do. Duncan, before we jump into the full interview, is there anything you'd like to add?
A related piece of that is he talks about how when you're doing statistics, you should be thinking about your procedure as something you will do over and over again. And I think a common failure mode in the evaluation harness in ML is not realizing that you're realistically going to peak at your kind of holdout set over and over again, and that you've got to find ways to defend yourself against that peaking and penalize yourself for doing that kind of peaking. But that's a really common mistake that I've seen both amateurs and pros make.
I appreciate both your insights there, and I'm really excited to jump into the interview now with Andrew Gelman. Hey there, Andy. Nice to see you.
Nice to see you too.
So, you've written and spoken a lot about how statistics, while important, may actually be the least important part of data science. So, I'm wondering if you could elaborate on this idea and share what aspects of data science you think take precedence over statistics.
Well, in some way, it depends on what you define as statistic. With data science, most important thing is the data quality and that you're measuring something close to what you care about. And then the next most important thing is representativeness, that the data you have represent the population in some way. Then statistical methods are used to adjust for non-representativeness or used to quantify uncertainty. Those things are a little less important. On the other hand, if you consider assessment of data quality and data gathering as part of statistics, then statistics is super important part of data science. But what's in statistics books is usually about data analysis, which is important, but not as important as data quality. Statistics textbooks often will say things like you should have random samples, but real life samples aren't random, so that advice isn't always so useful. In some ways, statistics isn't special in that way, like all fields are that way.
You've also made the point, though, that data science, at least in an industry setting, has a lot of other aspects, such as dealing with infrastructural concerns and cloud computing and that type of stuff. And those things we don't classically think of as statistics, but perhaps should, right?
Yeah, certainly working with the data is going to be super important. Being able to look at the data. So yeah, these are kind of computer skills. And computer skills are probably more important than math skills. Math skills can give you useful insight. So you really want to have both. But if you have, I think, let's say statistics training doesn't seem to be as important to me as other skills when it comes to data science. On the other hand, statistics is important. We see lots of bad work being done because people are not summarizing uncertainty appropriately, because people are dealing with bad measurements and don't have any way of thinking about that, or people have non-representative samples and they don't have ways of thinking about that either. So I think statistics contributes a lot, even if it's not the most important thing. I think without formal statistics, you end up relying on concepts. So someone might not ever have taken a statistics class, but be able to do reasonably well, but only if they're already thinking about it the right way.
That makes sense. And I love that you framed it. I'll paraphrase that computer skills, computational skills are more important than math skills. Because I hope we get to chat about one of your papers with Aki Vatari, what are the most important statistical concepts of the past 50 years. But one of the concepts you talk about is the bootstrap. And as you may recall, my background's in the biological sciences, where when I was working there, we would be taught the central limit theorem through the calculus, through the mathematics, which is totally opaque for a lot of people, right? Whereas if you teach it through the bootstrap and you do your resampling, you actually see the central limit theorem emerge in certain cases immediately, right?
Oh yeah, well, simulation's super important. My colleague Bob Carpenter, well, computer scientists in general call it experimentation now. So we have some idea and let's do some experiments. Let's simulate some things, and you want to do that. No, some math is useful too. So for example, years ago we did some calculation of what's the probability that your vote is decisive in the election. So your vote is decisive if the election is a tie without your vote, or within one vote of a tie, so your vote throws it into a tie. Like, either one of those two situations, you have a kind of 50% chance of swinging the outcome. What's the probability election is tied? There's a lot of bad calculations and the literature on this dating through decades, where people try to come up with mathematical distributions. They use the binomial distribution or this or that, and they give answers that make no sense. There was one published estimate that the probability the election is tied is 1 in 10 to the 90th. That makes no sense given that there's been a lot of elections that have been decided within a few votes. Even national elections have been decided within a few hundred votes sometimes. So it's innumerate to say that. But people didn't really know what to do about it. After a while, we realized that the appropriate way of thinking about this is as a forecasting problem, that the probability the election is exactly tied, so your vote is decisive, is not a statement about the electoral system. It's not a mathematical statement. It's a quasi-empirical statement. It's an empirical but probabilistic statement. So based on what we know about the election, how likely is it? Would it be exactly tied? And we can do election forecasts in different ways. And to get this number to within an order of magnitude, it doesn't matter too much what your forecast is. The probability your vote will be exactly decisive in the national presidential election is basically zero if you live in California, but it can be as high as 1 in a million or 1 in a couple million if you live in a swing state. So how do you do that? You can have a forecast. It's an empirical probability. So does that mean what you do is to see that the probability is 1 in 2 million, say, just simulate 100 billion election outcomes and then count how many are exactly tied. 100 billion can take a while to simulate. Also, you might be interested in computing this for other elections. So you don't have to do that. You can simulate just, let's say, 100,000 elections and count how many are within 1,000 votes being tied. The probability it's exactly tied is 1 out of 1,000 of that. Because for mathematical reasons, we know, given the precision of our model, that the distribution is flat over a narrow range of 1,000 votes. So a lot of problems are like that, where the solution has 3 steps. It has empirical statistical modeling, it has computer simulation, and it has the mathematical understanding that allows you to avoid a brute force calculation, which will itself be noisy.
And so what I'm hearing there is that data scientists to do this type of work and the power of simulation, that this is a wonderful example of how powerful it can be. But they don't necessarily need to be master statisticians or understand machine code, but having a certain subset of these skills helps them answer questions like this, right?
Yeah, it helps if someone's done it before too. As I said, I'm sure other people did reasonable things, but when I looked at the literature on this years ago, nobody had done anything like this. That it wasn't really taken to be an empirical problem, and that was a bit of a conceptual leap. On the other hand, once we've done it or someone's done it, it's not hard for other people to do similar things for their models.
And that's why I really appreciate conversations like this and putting them out there, because people learn this stuff on the job as well. Like, you get into a research institution or a particular company, and a lot of these techniques are siloed.
I learned it on the job.
Yeah.
Nobody taught me how to do it.
Yeah, totally. That's one of the reasons I think your blog has been so helpful to a lot of us as well, because you take the things you've learned on the job and put them out there. And we've touched on the importance of Bootstrap, generally simulation-based inference. And I'll actually, in the show notes, I'll link to your paper on what are the most important statistical concepts, where you also talk about the jackknife, cross-validation, these types of things as being useful. I am wondering, so we've identified this can be useful. What other statistical concepts do you think can be useful for data scientists to know about?
I think that statistics, I think the concept of generalization is very important. So we say this at the beginning of our book on applied regression and causal inference, regression and other stories, that we're generalizing from sample to population, or a sample is just a subset. So you're generalizing from observed data to what you care about. In statistics jargon, from sample to population. It doesn't have to be a random sample. We're generalizing from control to treatment group, which means for causal inference, we want to make a generalization or a statement or a prediction about what might happen if you got the treatment compared to you getting the control. It's a prediction or a generalization. Finally, generalizing from observed data to underlying constructs of interest. So that might be the generalizing from the survey response to the behavior you're actually interested in, or even the other way around, generalizing from a behavior to make inference about someone's mental state or anything like that. It just comes up all the time much more so than is traditionally described in statistics textbooks. For example, if you do an experiment in January on your customers, and then you are interested in just looking at how effective your treatment will be in the future, you're actually generalizing from your sample, which is January, to your population, which is existing in February, March, April, so forth. So everything has this kind of extrapolative flavor. And so I think of adjustment as being a very fundamental statistical idea. The other thing is something that you said already, which was simulation. That's that being, I have a rule now, I don't like to ever gather data until I've simulated data first. And it takes work to write a simulation. I always say this, that to analyze data is like playing Sim City, and to simulate data is like writing Sim City. So it's more work, but it's worth it every time. It's the kind of work that makes you think harder about the problem. So, for example, if I simulate data, I need to define a population and simulate a sampling mechanism. So I have to make a kind of call, how different is my sample going to be from my population? If I'm going to say I'm gathering data in January to make inference in February, I need to put down some model to simulate fake data. I need to put down some model of what's going to change. So I need to make an assumption. If I'm simulating a treatment, I need to make some assumption about a treatment effect. So suppose that you're considering an experiment. This is something I talked about in class the other day. You're designing an education experiment, and you have a new way of teaching, and it's supposed to improve students' test scores. You're going to measure their score. They have a test, the final exam. It's on a scale from 0 to 100. Okay? How large do you think, and you're going to estimate the average treatment effect as a start. That's what we do in statistics usually. Right? Okay, I'm not going to talk about causal identification or bias or random assignment or anything yet. I want to ask you, how large do you think the treatment effect might be?
And remind me, what's the experiment?
It's a new way of teaching. You're teaching some class, like maybe introductory statistics, and somebody offers you a new teaching regime, and you have some reason to believe it should be effective. It's not just the same textbook but a different color or whatever. It's a legitimate thing, supposed to work. It's not cheating. It's not giving people the test answers. It's just a better method of teaching. How effective do you think it might be? Give me a number.
Let's say a few percentage points. 3.
Okay, so
2 to 3.
So maybe. Okay, so let's try to think it through. So the scores go from 0 to 100, but okay, the actual test scores in this class, maybe they're mostly between 50 and 100, because that's the way final exams usually are. And then you think about it and say, how much it might improve your grade. Like, so if the average, let's say, is 75, and let's say there is a standard deviation of 10, so that 95% of the grades are between 55 and 95, sounds right. So the mean 75, a standard deviation is 10. It seems doubtful that the effect would be as large as 10, because that 10 would be taking you from an average student to someone on the top end of things. And teaching methods are great, but is it really going to do that? Maybe not. So let's suppose it's a pretty large effect and it's 5, okay? That's not the effect yet, because that's the effect, okay, if it works. But I think maybe half the students in the class are not going to be affected at all, because they're not learning through how you're teaching. They're actually just reading the book and doing the homework, or whatever it is. It's the same way as if you have a marketing plan, half the people weren't even watching TV when it was shown. Okay? So that takes us down to 2.5. Now, 2.5, that's a reasonable treatment effect, maybe. But now you think about it, there's going to be some people, the treatment, it's on them, they're there, but it just doesn't work, right? And they're 2.5, it works. So then you think maybe 1.25, because I think it's somewhere probably, if 2.5 is a reasonable effect size, and the average effect size might be about half of that. So I would expect a treatment effect of about 1. Well, that's a lot of reasoning, and I could be wrong. It may be too pessimistic, but first, the time we spent doing that was not time wasted. Second, if you really believe this, you would need a high precision experiment, Now, to get your standard error down to 1, you'd need a lot of students, or else you might need some good pretest measurement. If you have good pretests, then when you include them in a regression, it reduces your variance a bit. Not by that much. Like if your R squared is 50%, it reduces your variance by half, right? And R squared is 50% is a high R squared for things like that. The other thing you might have to do is have a more focused exam and say the exam score is noisy, but this is going to be more targeted. Or else you might say, look, realistically, an experiment of the sort I might design is not large enough to estimate the effect I want to do. There's nothing wrong with studying it, but don't run the experiment and hope things are statistically significant. Or even worse, run the experiment and then find something statistically significant. That would be a mistake. In theory, I didn't need a computer to do that. In fact, we did this calculation in our heads without a computer. However, it is better to simulate data. There are these sample size formulas, but they're a little too glibly used. I think it's important to really simulate the data. Also, you don't have to simply do averages. So if you want to do things like the regression or whatever, it's all simulatable. So yeah, you game it through and then you have to decide what to do. That's a lot better than saying, hey, I have this great idea. I have a couple hundred students. Let me try it. Let's do a randomized experiment. That's good. And that's not, I think that would be a mistake.
Yeah, I love that because I'm hearing several things in there. Firstly, of course, simulating is important. We did a mental simulation, not a computational simulation in a lot of ways.
Well, we did.
Right?
I'll say that we simulated the effect size, but we didn't simulate the data, right?
Correct.
Simulate data would allow for additional variation.
Absolutely. And what we engaged in was some form of like first principles thinking through the data generating process as well, which is incredibly important because we do make assumptions like that. I always joke that I'm probably a Bayesian with very high likelihood, I think. But one thing that I do love about Bayesian inference is that it forces us to make our assumptions concrete and make the data generating process concrete. What you also did in there was some form of power analysis, essentially. So these are several things that I think are coming out that are important for data scientists to be aware of if they're thinking of doing experiments is first principles thinking, data generating process, simulation, and some form of power analysis as well.
The thing about, I prefer the term design analysis just because power is associated with hypothesis testing. The thing is, I think, to do it in a forward rather than a reverse direction. To not say, I'm supposed to have 80% power and this is my sample size so I can detect an effect size this big, right? And I think that's very logical, but I think it's missing something, which is the sense of what's a realistic effect size. And that's a kind of reasoning. I've done this many times. Many times I've been in the room and I ask people what effect size to imagine. And they say, we don't know. That's why we're doing the experiment. And then I say, then we talk it through. And you can often get some reasonable number out. It's surprising. Like you have a lot of prior information there, which you don't realize. And again, it's not, even my own textbooks, we don't really talk much about that. We tends to be mathematical, or we have weak priors. We don't really talk about it. We use defaults. I think there's so much there if you, as you said, if you work through the process.
For sure. Something we've been dancing around is causal inference. And I do want to chat about it explicitly. I do think industrial data science hasn't imported enough tools from econometrics that's probably my hot take. I know you're a huge fan of counterfactual causal inference. And actually, I know you don't rank order them, but it's the first point in your what are the most important statistical ideas of the past 50 years. What can data scientists learn about counterfactual causal inference that could help them in their work?
I think that the concept is that causal inference is predictive statement. So you're making a prediction about what would happen to a particular person in a particular scenario if you did treatment A versus this person in this scenario if you did treatment B. So I like that because it doesn't, you're not starting with a parameter. You're not saying there's this thing called theta that I'm trying to estimate, that I'm trying to get an unbiased estimate of. You're really saying the causal inference it's two predictions. It's what would happen under the treatment, what would happen under the control. It's just, and you could subtract the two if you want, and then you can call that a causal effect. But In my mind, you need a model. And often to say you need a model, you need to actually have a model for what the treatment is. People have these examples. What's the effect of a certain exercise regimen on some health measure? And well, it depends what else you're doing. Like you could say all else equal, but that doesn't even mean anything because the exercise regimen takes time away from other things. Also, you're probably going to be eating differently. Maybe do you want that to be the same diet or not? You have to define it. There's not an answer. There's no true causal effect. There's no answer. What's the effect of having more cops on the street on crime? Depends what crime, it depends how the cops are being on the street, it depends what the alternative is, it depends where it's happening. And I think a lot of times we make the mistake of thinking we're trying to estimate the causal effect as if it's this thing like the speed of light, that it's a number, a constant. But it varies. It's more like the speed of sound, I guess.
So, actually, with all these techniques we're talking about, last time we did a podcast in the before times, we talked about your work in polling, and I think that's relatively topical right now with the election coming up. And I think perhaps
What, you often
we talked
election
about.
too?
Actually, we had local elections last week, and I my hot take is that people don't pay enough attention to local elections in Australia, and they pay more attention to the US election, whereas the local elections impact our lives a lot more, and we're eminently distracted.
From our perspective, all the elections in Australia are local elections, so that's not right.
Absolutely.
We wrote a paper about why it's rational to vote. As I said, I talked about the probability of your vote making a difference. In the US presidential election, if you live in a swing state, that's like good news for you. The politicians are catering to your vote in some way or another. Your chance of casting a decisive vote might be 1 in a million at best. Well, that's great. 1 in a million is pretty small probability. And that's at best. Like typically it might be 1 in 10 million or 1 in 50 million. So then the question is, why vote? If you think of it as a decision problem, if I vote, it takes maybe an hour or a half hour, however long to vote. You have to educate yourself, decide who to vote for. There's blah, 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 blah. It takes a little work. And then the reward is a 1 in a million at best chance of your vote making a difference. But yet people vote. And so there's some question. There's lots of reasons why people vote. Like, you don't have to do something for rational reason. You do it because you want to. Why do people go to the movies, right? They're not making money out of it. They're getting entertainment. You're not getting entertainment out of voting, but you feel that the traditional term is you're satisfying your civic duty, so you feel good about yourself. Fair enough. However, if you think about it, there is actually a direct benefit of voting, not a mere psychological benefit. And it goes like this, that the relative utility of an action is equal to the probability times the relative gain if the outcome happens. And so if you go to vote, put in the effort, there's, let's say in best scenario, 1 in a million or maybe 1 in 10 million chance of your vote making a difference. If your vote makes a difference, what's the impact? It's not going to make you $10 million, right? Unless you're a rare billionaire who might get a tax cut, right? But for most of us, the direct instrumental benefit from voting is small. However, that doesn't mean the total benefit is so low. You might reasonably feel that this candidate will be better for the country and even the world as a whole, right? Peace and prosperity, right? We've seen different things happen, and there is such a thing as bad leadership and good leadership, and the outcome is stochastic. But it's not unreasonable to me to think that my preferred candidate could make a difference of, let's say, an average $1,000 benefit for every American. Between economic benefits, health benefits, the future, all sorts of things that can be happening. Put it together. Let's say it's $1,000 per. Not just, and I don't mean $1,000 like people would be that much happier that their candidate wins, because then you have all the millions of people who will be unhappy. I'm talking about their quality of life going forward, right? You think candidates better for the economy, better for peace, better for health, better for freedom, all these good things. Let's, for convenience, put things on a dollar scale and say 1,000. That means the benefit in the U.S. for the U.S. as a whole is $330 billion, right? Now, I can think if I vote, it's like buying a lottery ticket, and it costs a small amount, like a few minutes, an hour maybe, to go and vote. I have a 1 in 10 million chance of that lottery ticket winning. And if it wins, I essentially am get to donate $300 billion to charity. I would do that. I would take that bet, right? $300 billion to charity isn't as good as $300 billion just for me. I could spend it on Stan. I could really use it effectively, but still making Americans better off. I'd be very happy with that. It's worth it. So I think it's actually rational to vote. Now, I say this because you brought up local elections. So in a local election, your probability of being decisive is much higher because there's fewer votes, and the benefits are correspondingly lower because there's fewer people being benefited. Maybe the overall number is comparable. Maybe it's a little lower for a local election because for a national election, you're benefiting more people, but also the benefit per person might be larger. Just because the president just has more influence than your mayor or whatever in terms of even the local people's lives. It depends, right? But so there's a kind of logic to saying maybe voter turnout should be a little lower in a local election because it's a little less important, even though your probability of making a difference is higher. We did some math on this because if nobody votes, then it's really rational to vote because your vote will be decisive. So you can work out that there's an equilibrium point. No matter, it depends on people's utilities and how much it's important for them, what they consider the utility for them of having their preferred candidate win. But given a distribution of utilities, you can derive an equilibrium voter turnout rate, which is cool. I liked it. I like this paper. It's all theoretical. I don't think real people vote exactly for that rational reason. Like, I think people vote because it seems like the right thing to do. However, that doesn't mean the rationality is irrelevant because there's an indirect thing. One reason we vote is because there's a lot of publicity. One reason there's a lot of publicity is because the stakes are high. And if it was irrational to vote, that would show up as campaigns realizing that there was no point in swinging people's vote. Then they wouldn't campaign as hard, and then we wouldn't care as much, and we wouldn't vote as much. It's a little like economics, like the, as if reasoning, right? You're not making decisions based on maximizing utility. However, to the extent that you can model, that can be an accurate descriptive model, because often implicitly people's behavior can be described that way. And so similarly with the voting, if it were really true that the chance of the election being tied were 10 to the minus 90, then nobody would be campaigning at all. And that's not the case. So it all fits together. And so I like that model, and I enjoy math.
Yeah, that's a great example. Of course, there's additional utility in Australia where we get fined for not voting.
Yeah.
And they make it easier by having elections on Saturdays here. And often they'll have barbecues to incentivize people to come and vote. I think we can tie together a lot of things we've been talking about by one of the most important statistical concepts you mentioned data scientists should know about is being able to generalize from a sample. Now, this is incredibly important in polling, as you've written extensively about. Also, our mutual friend Shira Mitchell works for Blue Rose Research.
Shira worked with us on a project, speaking of causal inference, a retrospective evaluation of the Millennium Villages project. And the Millennium Villages project was an international development project that had been done in several different countries in sub-Saharan Africa. And it had been done, and afterward, it was a 10-year program. And afterward, there was an evaluation of some sort, but then people were concerned because there was no control group. It was just one of these things that it would have perhaps been difficult to set up a control group when the original study had been set up for political reasons. So we created something called a retrospective control. We went back in time to the beginning of the study in 2005, I think it was. We went back in time and created a bunch of control villages, which were similar to the treated villages, but not treated. We found a lot of matches and randomly selected from them. We didn't literally go back in time. What we literally did was only use information available in 2005 to make this assignment. And then we followed them up and then did this comparison, which is like, you always have to be concerned that there could be systematic differences between the two groups. But I think we did a pretty careful job on that and found some small effects. That was the project that she ran. That project, I helped with that, but she was the leader.
Very
of
cool.
that.
So what they do now is they help campaigns make higher quality strategic decisions, and democratic campaigns, by they say democratizing access to accurate measurement. I suppose I have two questions for you, and I'm breaking the cardinal rule of not asking two questions at once. But firstly, why, in terms of polling, we're aware that we want to generalize to the entire population. Polling seemed to used to work and doesn't work as well now. So why is that the case? And secondly, how are these types of techniques we've been discussing applicable to organizations such as Blue Rose, trying to help campaigns make more strategic decisions?
Polling, why do you say polling doesn't work as well as it used to? I'm surprised that you say that. What makes you say that?
I could be totally wrong. It seems polling is something which used to be quite effective. We, of course, have many examples, but I suppose Nate Silver's predictions during Obama's election was as accurate as you can get. And since then, we've seen some fall off from the ability to make such accurate predictions. I could be wrong, though.
Yeah, I think you're wrong, but you're not the only person to be wrong, and polls are not perfect. I think first, okay, if you do an opinion poll about how people plan to vote, you're asking people how they plan to vote now, and the election's not going to be now. So people can change their views. Also, the people you don't know who's going to vote, and turnout is itself unpredictable. Beyond that, we've looked at poll data, and there's systematic non-sampling error. So we took a bunch of polls from, I think it was like 2000 to 2016, state level polls for governor, senator, and president. We took a bunch of these polls, and we only took polls that were in the last, I think, 2 or 3 weeks before the election, when there was very little movement. For each poll had an estimate and a standard error, but then you can look at the empirical error of the poll. That is, you can literally compare the poll estimate to the actual election outcome. Again, they don't have to be the same thing. The poll is a survey response; it's not a vote. So you wouldn't expect them to be the same number, even within sampling error. So it turns out that if you look at those, the actual polling errors are about twice as large on average as the standard errors, the sampling errors. So there's a lot of non-sampling error also. And indeed, that's always been the case, though. That's not new. I think the difference is people expect more. So when I was a kid and there'd be an election, there'd be a poll and they'd say, Ronald Reagan, whatever, is at 52% in the poll and with a margin of error of 3%. It would be like, that's what they would report. And then they would say, yeah, he's ahead. That's where we are right now. No one was going to make a statement from that, like he's going to win, he's going to lose. You took the poll statement as a piece of information. Now, sometime between then and 2008, I guess there were more and more polls, and then people started to say, if I average a bunch of polls, then the standard error goes down. But of course, it doesn't reduce the bias when you average a bunch of polls. It just reduces the variance. So then people just, I think, were trying to demand more. But if you look at polls from 50 years ago, the poll right before the election could often be off by a few percentage points. It's just that it wasn't like was expected that would be the case. A candidate could be ahead the day before the election, and it wasn't like everyone was all sure it was going to happen. A certain level of confidence arose, and then now people want more, and they want to know who's going to win the election now. I don't know who's going to win the election, right? People haven't voted yet, right? People haven't decided. The other thing is that to the extent it's harder, it's always about signal and noise, and the noise is no higher than it was before, but the signal is less, in the sense that election to election, we've had a series of close elections. Right? Like every election since 2000, except for 2004, the Democrats won by between 0.5% and 2%. In 2004, the Republicans won by a couple percent. They've all been very close. And if the election's going to be that close, what did Biden win by maybe 3 or 4%, something like that. Even that, he won decisively at the national level, but it wasn't by that much in historical terms. If the election's going to be close, then it's going to be hard to predict the winner because it's inherently difficult with the uncertainty. And so people are asking for a level of precision that's not realistic. If it were 1996 when Bill Clinton was cruising to re-election, then we'd be having the polls and we'd say the polls are very clear. Or Ronald Reagan winning election by even much more than Bill Clinton did, then it wouldn't be an issue.
I love this because it speaks to something we've been dancing around a bit, which is actually understanding uncertainty and how to communicate around uncertainty and interpret uncertainty. So maybe you could just speak a bit to how you think statisticians and data scientists really need to deal with uncertainty and think about it in their jobs.
I'm uncertain. There's been research that I think the most celebrated research in this area has been by the psychologist Gerd Gigerenzer and his crew. They have this one thing they push is the idea of natural frequencies. So instead of saying 2% of people believe blah, 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 you'd say if you had 100 people in the room, you'd expect 32 of them. Or if you talk about, they have these famous like puzzles where the disease rate, there's a disease, it's a very rare disease, and then you take the test, and the test might misclassify, and so because of that, if you test positive, it doesn't really mean you have the disease.
So it's the base rate fallacy, essentially.
I wouldn't, whatever, it's a probability problem. You typically framed as a probability problem. Base rate fallacy has its own kind of jargon meaning, so I won't quite go there. We could talk for an hour about this stuff, this psychology of uncertainty. Yeah. It's super interesting. It's also famous because there's been a lot of bad work in this area too, a lot of overstatement, where paradoxically the people who study uncertainty don't recognize the uncertainty in their own research, and it doesn't always replicate. Lots going on. But let me just say this, that it's a very tricky problems. You have it's a disease. 1% of people have the disease, and then you take a test, and the test has a 5% error rate. You test positive for the disease. Then what's the probability that you actually have the disease? And it seems like it should be about 95% because the test has a 5% error rate. But given that it's a very rare disease, it's actually quite likely you don't have it. And that always puzzles people. But the way that they like to explain it in natural frequencies is you say, imagine of 1,000 people. Out of 1,000 people, 10 have the disease. 990 don't, right? And then people get the test. And then 5% of the people who get the test, the test is 95% accurate. So of the 10 people who have the disease, they're probably all going to test positive because it's of the 990 who don't have the disease, 5% of them, so about 50 of them or so, or 49 or whatever, are going to are going to test positive just by chance. So you look at those 1,000 people, and it includes 10 people who are true positives and 50 false positives. The chance that if you're like at random in that population and you test positive, you're probably not. I like that. That's this natural frequencies idea. That's a very specific, famous example. That said, it's not the whole story. There's a lot of people just don't think quantitatively. I think that quantitative thinking is just an unusual. I did an activity today with my daughter's 8th grade class, and I was talking about elections and talking about how old you have to be to vote in the election, and should older people get to vote, should younger people get to vote. And I don't know how we ended up we ended up talking about death rates and actuarial stuff, like what's the probability that you live another year. And so the teacher was 41 years old, and I asked the students, what do you think the probability is that he'll live another year? And someone said 50%. So really? So no, it's 90%. I said, wait, so this school, if you took 10 teachers out of this school, you think one of them would die next year? But the school has more than 10 teachers. Are teachers like dying every year? Do you hear about this? And it was hard. Like the actual probability he lives another year actuarially is like 99.7% or something. Don't quote me on that. But we looked it up from the Social Security database, life tables. It's easy to get that information. But like people don't think quantitatively. Famously, surveys, they ask people about minority groups, and whatever minority group is, people overestimate. They think that 25% of Americans are Black. They think 25% of Americans are Hispanic, Jewish. 25% of Americans are gay. They think 25% of Americans are transgender. Like whatever you ask, it's 5%. That the psychologists call this the super additivity phenomenon. That the probability is up to 100%. But you can enforce it. Like you can give them a little wedge on the computer and say who are the white people, who are the Black people, and make sure it all adds up. But if you don't do that, people get. So I don't know that natural frequencies would solve that. I just think numbers are not so intuitive to most people.
Numbers aren't intuitive. Probabilities are even less intuitive. I think I like this idea because it's helped us once again go through first principle thinking with respect to even the way you spoke with these children. Hey, would you think this would happen? Would you think that would happen? And figuring it out that way. And also through the natural frequencies, performing some sort of mental simulation, which you can do computationally as well. So these two things as ways to deal with uncertainty as well, I think are fantastic. We have talked a bunch about the types of statistical techniques that are important from the past 50 years. I'm just wondering, in the spirit of forecasting, if you can speak to what types of statistical techniques you think will become more and more important in the coming years.
I guess you should probably ask people younger than me about that. Who am I to say? There are tools that I find useful. There's this something I've called the methodological attribution fallacy, which is that I think good statisticians or effective statisticians will attribute their success to their method, maybe more than they should. I remember years ago, Brad Efron gave a talk and he had some kind of complicated approach. He was bootstrapping something. And I felt, to me, I always feel like I like bootstrapping. I'm just doing a research project now where we're using it to do survey adjustment. I'm using a weighted bootstrap. It's great stuff. But often, there's the way bootstrapping works is there's an estimator and then you bootstrap it. And I said to Brad, like this years ago, like I think all the actions in the estimator. I think the bootstrap part is like fine. It's a billion ways of bias correction, a million ways of getting uncertainty estimates. Like using the computer is great. You don't really have to be because his talk was like 99% about the bootstrap, like 1% like, oh, blah, 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 here's the estimator. Now, it's a very complicated problem because it wasn't independent data. There was inequality restrictions. It's very clever, complicated. I don't buy it. I think you could brute force the simulation. The bootstrapping isn't so important. And he said, I talked to the astronomers and they find these permutation tests, permutation properties very convincing. Like to them, it really works. And it's really not just it gives a good answer, but it makes sense to them. And that's fine, but it reminded me of when I talked to Don Rubin, the great Bayesian, who would say, everyone's really a Bayesian. They, even if they don't admit it, they're thinking when you give them a confidence interval, they interpret it as a Bayesian interval. And I just thought, okay, Brad, when they were talking with you, you're very convincing, and I believe that they think everything in terms of inverting permutation tests. And Don, you're a bright guy too, and I think when they talk to you, they're talking your language and so forth. I use more of Don's methods than Brad's methods, although I use both, but I think that they took a little bit too much evidence from their collaborators. They're a little too quick to say their method really comports with what science is like. But I do that too, like I told that story we had about what's the effect of doing the simulation and saying how effective is the treatment. Like I said, that's really good because to do science, to do engineering, it's good to think this stuff through. But who knows? Maybe if I'd given you a whole speech about bootstrapping and inverting hypothesis tests and how what you really need to know is asymptotics, I might have been able to make a convincing case and say, really, asymptotics is important because you're imagining what would happen if you got enough data. And really, like, ultimately, that's the question you'd want to know is what's the truth if you had an infinite sample size, blah, 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 blah. I could do it. Like, it would be harder because I'd be faking it. But, like, someone who works in that area could do that. And so I feel like I'm a good person to talk about why my methods have been effective and how to use them better. but maybe not a good person. I don't know who is, but I don't know that anyone's a good person to say what's the methods of the future, at least maybe not somebody my age.
Which of your methods would you like to see garner more adoption?
Maybe I should say, which of my methods would I like to see garner more adoption by me? I would like to be using more informative priors, and I'm working on it, but I would like to better integrate my data analysis modeling workflow. I would like to not always be in the position of searching through my directories and trying to find data. I'd like to be able to answer statistics questions without somehow feeling that I'm starting from scratch each time. It's hard to know. I'm atypical in the sense that I do research, I do applied research, I do theoretical research, I teach, and I write books. And so even when I'm doing partly when I'm teaching or writing books, I'm trying to have realistic examples and work things through. But then I get in the habit. So when I'm doing a research project or consulting project, I tend to do it in the way that I might write a textbook chapter. Of course, it makes me a better researcher because I do projects and my research articles look a little like textbooks and my textbook chapters look a little bit like research articles. But I think that's good, but I don't know. I often just feel there's something about my workflow that's awkward, that I don't have a fully integrated. I'll stop and do a simulation and then I'll write something up. I don't know if there are better ways of doing it, but that can limit what I work on. I tend to work on problems that are fairly small because I can handle the data. It's not so much computation time as just like I feel I get insight that way. That's my skill. I keep analyzing the 8 schools data, which is a bunch of experiments from the late 1970s, and I continue to do more with it. Unfortunately, I don't have the raw data, or I could even do more. But like the smallest example, I'm often doing so. I did something in class, which was all about the probability of the election. It had to do with mapping the probability of the win probability to the expected vote, and we did it in class. And now I want to write it up for the blog, I think, and so I'm always thinking in that way. But that does mean that I tend to work on smaller problems and get insight that way. And so I have a lot of respect for the people who do the big stuff, write the computer program that can play ping pong or whatever. It's like just a different world. I do think that the work I do can be useful for those people too, in 2 ways. One is they can literally be using my methods. They might be using hierarchical modeling or Bayesian computation or STAN or whatever. The other thing is that there's often a last mile problem in statistics. Like you might see something where people are evaluating a bunch of high-tech machine learners, each of which uses power consumption of Iceland or whatever, like this horrible, like evil stuff, right? But then they do it, and at the end they're saying this method is statistically significantly better than that method on these examples. So and the last mile, they're doing small data, they're doing and they are like all my insights and understanding of these small problems can be very helpful because at the end of the day, you're talking about that can be measured and studied. So I think there's definitely always going to be room for that.
Something you've spoken about, which I love, is how us as data people and statisticians are good at fooling ourselves. So I'm wondering if you can speak a bit to how statisticians most often fool themselves and what we as data people can do to stay grounded and avoid these pitfalls.
Maybe I fool myself less than I did before. I think probably I'll give a kind of procedural answer, which is like that probably a good way to avoid fooling yourself is to put yourself in a position where fooling yourself is costly rather than beneficial to you. So if you know ahead of time that you're going to do a replication study or someone else is going to do a replication study and you're going to respect that, then actually that reduces your incentive to come up with a wrong answer right now because it'll make you look stupid later. The other thing is I always tell this to students, if you develop a method and say this method's better than the old method, no one will believe you and they shouldn't because almost nothing dominates. What you really want to say is what's the domain of domination or applicability of this new method. And to do that, you have to figure out where it doesn't work. You don't really understand something until it stops working, and you don't understand a machine until you can break it, and so forth. And so in our research, our applied or our theoretical research, we should be we have not succeeded until we've succeeded in breaking it. So we have an actual motivation to do that.
I love it. So to wrap up, we've talked about a lot of different statistical techniques, of course, non-exhaustive, but I'm just wondering from this conversation and anything else that comes to mind, what are 3 concrete ways in which data scientists can improve their work by incorporating more statistics into their practice?
So number one is fake data simulation or simulated data experimentation, which doesn't just mean writing the program to simulate the data. It means creating the world. It means thinking it, like going, instead of just saying alpha and beta, you have to put numbers to alpha and beta. It's a little bit intimidating. It's not something that you've usually been expected to do. Even in statistics textbooks, when they have examples that the numbers seem to be just don't come from anywhere. So that's number one. You want 2 or 3. So everything's about communication. You know the saying, your closest collaborator is you 6 months ago, and she's not answering email. And you need to always be communicating. For example, statistical graphics. I find that the tools of presentation graphics are good for research graphics because things like labeling your axis, it's good if you're own to understand your own graphs. When I make graphs, it's good to have multiple plots per page. You often see people, I'll just say this for workflow, people are on their laptops and they'll have one window open and that's it. Like the window takes up the whole screen or 90% of the screen. It's great to have multiple windows. You can have the text editor, you can have your coding, and different things can be happening. If you have a good, what is it called, an integrative development environment, that can work. But even then, like people, when you're not doing that, when you're just like looking stuff up on Google, on the internet, and then writing a document, have the document and the Google each take up half your screen so that you don't have to go back and forth. That sounds silly, but I think that, of course, I could give advice like version control and stuff like that, but you have other people to tell you things like to give advice like that. But I think that it's almost always good to, like in statistics, they say anything worth doing is worth doing over and over again. Statistics, I have these sayings, like one saying is that theoretical statistics is the theory of applied statistics. Another saying is that statistics is frequentist statistics, meaning frequentist in a good way means understanding the properties of statistical methods that are applied repeatedly. And in statistics, we apply methods repeatedly. You almost never do things just once. If you're a textbook writer, that's really true. But even if you're just doing your project, you're probably going to be using that method again. Statistics is the science of defaults, and you have to think about what that means. Put yourself in that position. Just as in coding, they always say never write the same code twice. If you're going to do that, wrap it in a function. But that's true of statistical procedures too. Do not think that, even if you're not writing a textbook, pretend you are. Do not think that you are, whatever you're doing only once. Assume you're going to be doing it more than once. Partly that means documenting it and all that, but also it means thinking about what it means. It means thinking about what its inputs are and so forth. So that's like thinking like a coder in some way.
Yeah, absolutely. So simulation and building your world, building SimCity, thinking like a coder. And I'll throw one more in that I love from this conversation that I'd love just 30 seconds from you on: the importance of counterfactual causal inference.
Sure, that's definitely related to the simulation. It's not always arising. For example, if I'm doing survey research, yeah, if you're a campaign, you might have the counterfactual, what if we do this, what would happen? But often it is not counterfactual, but it's descriptive. So it's not that. But I will say this, I do think statistics is always comparative. That in statistics textbooks, they'll sometimes set up a problem. Your goal is to estimate theta, something. Your goal is never to estimate something. Your goal is to compare. If it's not causal inference, you're comparing two groups, or you're comparing men to women, or you're looking at changes over time, or you're comparing different countries. It's almost always going to be a comparison of some sort. Be aware of that.
I love that. It reminds me of, what's the saying? There are like only 3 types of figures: one showing something changing over time, one comparing several groups, and the third one, I can't remember what it does.
Well, there's a whole other story. Exploratory graphics is about learning the unexpected. But if you think about that, means that's a definition relative to the expected. So statistical graphics and exploratory data analysis is actually very connected to statistical modeling, because the better your model, the more sophisticated the expected is, the more you learn from the unexpected.
Great. And I hope we get to chat about that sometime. Andy, it's always a pleasure to chat with you, and really appreciate your time and wisdom.
Nice to talk with you too.
Thanks so much for listening to High Signal, brought to you by Delphina. If you enjoyed this episode, don't forget to sign up to our newsletter, follow us on YouTube, and share the podcast with your friends. All the links are in the show notes. We'll catch you next time.